Welcome back, everybody, to Probability and Analysis webinar. Today, our speaker is Don Minzer from MIT, who is going to talk about on the Fourier-Entropy conjecture. Please, Dor, feel free to start.
Thank you very much, Bata, and thank you all for coming to this seminar. So I'm going to talk about some recent results about the Fourier-Entropy conjecture. This is joint work with Esti Kalman, Guy Kindler, Noam Lifshitz, and Moli Safra. By the way, if there are any questions, please feel free to stop me or write in the chat or whatever you feel comfortable. So before we get to talk about entropies, let me tell you about the topic that we're talking about. This is a Fourier analysis on the Boolean Hypercube. So throughout the talk, I'm going to consider the Boolean cube, which in this context is ±1 to the n, equipped with a uniform measure. So of course, you can think of other product measures, but the focus today will be the uniform one. And we want to study Boolean functions, meaning functions f that map the cube to ±1. So given a function, there are a few natural and important notions you can associate with it. One of them is called the influence of variable, which is defined as follows. So for each coordinate I in n, I can define the influence of I to be the probability that when I pick an input x uniformly for the cube, the value that f gives to x and the value that f gives to x when I flip the ith coordinate of it is different. So this is naturally called the influence of I. And then if you take all of these influences and you sum them up, this is called the total influence of f. And the total influence of f is a very important and natural complexity measure function. It goes by other names, such as the average degree or the average sensitivity. So we may see later on at least one reason to call them average degree. But anyway, this is something that is very important to learn about. And in particular, a key question that appears in many contexts is to say something about a given function if its total influence is small. So I give you a function, I tell you that the total influence of it is at most k. What sort of structural result can you tell me about the function? I come from a TCS background, and this question is certainly important over there, but it's also important in a bunch of other areas, some of which appear on the slide. So really, this question and related questions is, I think, would fair to say what a lot of analysis of Boolean functions revolves around. And today I'm going to tell you some structural result along those lines. Okay, so before I tell you about entropies, let me tell you about two of the most basic results in the area. Those are the KKL Theorem and the Fourier-Entropy Theorem. So before we talk about theorems, let's talk about examples. So how can you come up with a function that has total influence at most k? Well, here is a very simple function. You take your coordinates x1 to xn, and you just output the first one. So this is called the dictatorship function because only one coordinate decides. This is the dictator. And you can see that the influence of variable 1 is 1, whereas all of the rest of the variables have influence 0, so total influence is 1, which is certainly small. But if you think about it for a moment, you can see that actually, as long as f depends on at most k coordinates in whatever way you want, it still has total influence at most k. So from these two examples, you can imagine that maybe functions with total influence at most k are functions that depend on at most k coordinates or something like that. And something along these lines is true, and this is the content of these theorems. So the first theorem is the KKL Theorem, which says the following. Suppose the total influence of f is small, is at most k, think of k as 10. Then in that case, there exists at least one variable that has a lot of influence. Namely, there exists a variable I whose influence is at least exponential in k. So a priori, you may hope for a polynomial bound, but you get an exponential bound, and this is actually the truth. This is the best you can do. So the way I want you to think about it is that if you have small total influence, you resemble a dictatorship. You resemble, in some sense, an example of the first type, because you have large influence. But this is a very kind of weak structural result. It only tells you something about correlation or something like that. So the next question is, can you get a stronger structure? Well, it turns out that you can, and this is the Fourier-Entropy theorem. So this is the formulation of the Entropy theorem. So it says that if I have a function f whose total influence is at most k, then not only do I have an influential variable, but essentially I only depend on 2 to the k coordinates. That is, I can find a set of influential coordinates, I can find a set of size 2 to the k, and some function on these 2 to the k variables, so that up to some noise, my function f is the same as this local function g. Okay, so these are 2 very fundamental theorems in the area, and they have many, many applications. But one significant drawback of them is that they really only have meaning when k is little of log n. Because if k is, say, log n, then this theorem tells me that I depend on at most n coordinates, but I don't need any theorem to tell me that. The domain is -1, 1 to the n. I know that I only have k coordinates. So this is the drawback. And in some sense, this is a significant barrier in the area. This is called the logarithmic barrier. I don't think that there is actually a name for it in the literature, but it's sort of well known that you can say a lot of things about functions with the great most log n, but essentially nothing after that. So kind of the result that I'm going to tell you about today is a result that is applicable beyond this logarithmic barrier, and it tells you some non-trivial structure result beyond that. So let me quickly tell you what we're going to see in this talk. So first of all, I'm going to give you a little bit of the basics of Fourier analysis on the cube. I'm going to formulate the Fourier-Entropy conjecture, and then I'm going to tell you about our results. And then in the second part of the talk, I'm going to try to tell you a little bit about how proofs go around these questions, and I'm going to sort of overview a proof of the KKL theorem and tell you in very rough broad strokes how do you get from a KKL type argument to our results. So of course I'm not going to show full proofs, but I'm going to try to give you the idea at least. Any questions so far? Okay, great. So basics of Fourier analysis. Well, so the very first thing you do is you look at real valued functions over the cube, and you think of it as a vector space equipped with an inner product. And for normalization reasons, in this talk, I'm going to take expectation inner product. So the inner product between the function f and the function g is the expected value of f of x times g of x, where x is sampled as a uniform point in the cube. So once you have an inner product, it makes sense to try to look for an orthonormal basis for your vector space. And indeed, here you have a very nice basis of characters. So these are the functions chi s. So for each subset s of n, I define the character chi s, which takes as input the vector x, and it outputs the product of xi, where I is inside s. So it's a standard fact, and it's not too hard to prove that if you look at these functions, they form an orthonormal basis for the space of real valued functions. So we're going to use them. It's a very good set. Okay, so we have a basis. So that means that if I give you any function, you can express it according to this basis, and this is called the Fourier decomposition of the function f. So given any real valued function, I can write f of x as summation over s, some coefficient times chi s of x, and this coefficient is called the Fourier coefficient of s, hat f of s. So this is so far very standard. And because this basis is orthonormal, there is a very nice formula for these coefficients. They're simply the inner products of f with the basis elements. Okay, so this is what Fourier decomposition is. And once you have this decomposition, you can start proving some very simple facts about it. So for example, as usually the case in Fourier analysis, if you take an inner product, this translates to an inner product up to normalization in the Fourier domain. So the inner product between f and g is the same as summation over s, Fourier coefficient of f times Fourier coefficient of g. And in particular, if I take f which is equal to g, which is a Boolean function, then I get that, well, the inner product between f and f is 1, but on the other end, by this fact, it's summation of the squares of Fourier coefficients of s. So in particular, I get that these squares of coefficients, they form a distribution. So if you remember the word entropy from the beginning, this is something that has to do with this distribution. So I'm going to soon state it. But yeah, using really nothing special, we got that this is a distribution. Okay. Good. So now that we've done all of that, I can tell you what is the Fourier-Entropy conjecture due to Friedut and Kalai. So here is the moral statement. The moral statement says that if I have a function f and the total influence of that function is at most k, then the Fourier spectrum of f is concentrated on at most 2 to the k many coefficients. Namely, if you ignore a bunch of coefficients, your Fourier decomposition is sparse. So this is the moral statement. But here is now the formal one. So it says that there exists an absolute constant C, such that if I take this entropy that is resulting from the squares of the Fourier coefficients of f, and I compute its Shannon entropy, then this entropy is at most constant times the total influence of f. And this holds for every Boolean function f. So reminder, the Shannon entropy is this expression. It's summation of the probability of s times log 1 over the probability of s. Here the probability is the Fourier coefficient squared. So if you work with Shannon entropies at all, you sort of imagine that this is something that morally resembles kind of where the mass of f lies. So this is why the moral statement above. But strictly speaking, this Shannon bound is stronger. So this is a very interesting conjecture. If it is true, it has a bunch of nice implications. So first of all, this would be the first structural result that would say something interesting about functions that have total influence beyond log n. The statement would be that if you have low influence, then you are sparse in the Fourier domain. It also implies a conjecture known as the Mansour's conjecture, which says something about learning of polynomial size DNA formulas. And also, which was kind of actually the motivation for this conjecture, it implies some sharp threshold results. So for example, it implies that for graph properties, you have a sharp threshold result which passes the one that you can prove by KKL Theorem. So this was solved by Boolean and Kalai already for graph properties, but in general, still the question remains open. Okay, so this is the conjecture, and this was open. This is still open for a long time, really without much progress. So people considered a weaker conjecture. So this is the Fourier mean entropy conjecture. I think that Rainer Donald was the one who stated it first, and it says, okay, so we're trying to prove that the Fourier spectrum of f is concentrated on 2 to the k many coefficients. So in particular, it says that there exists at least one coefficient that is at least 2 to the minus k in magnitude. So maybe let's prove that first. Let's prove that there exists one large Fourier coefficient. In notation, the conjecture, the mean entropy conjecture states that if you take the mean entropy of the distribution f at squared, then now this is at most c times the influence of f. So the mean entropy is the minimum of this log. So this amount is saying that there is at least one large Fourier coefficient. So this is a statement which is you can easily see to be weaker than the Fourier-Entropy conjecture, because mean entropy is always at most the Shannon entropy. But it is stronger than the KKL theorem. So this requires like 1 minute of thinking, but it's stronger than that. So it makes sense that maybe we try to prove something like that and maybe then move to the Shannon entropy. But this was just and still is wide open. So we don't know how to prove even this statement. Okay, so far I told you about a lot about what we don't know how to do. So what do we know how to do? Well, so I told you this conjecture has been around for a long time. So people tried a bunch of things, and I put here a few citations, but let me just say that it was proved. So several composition properties of this were proved. Several classes of special functions were studied, for example, symmetric functions, for which the conjecture is true. But kind of the most general result before our work was the bound that follows if you apply Friedrich's theorem, which would tell you that the mean entropy of the function is at most influence squared. So this is this very last bullet. So this is the state of affairs before our work. And what we showed in this work, or rather one of the things that we showed, is that if you have a balanced Boolean function f, then you can improve this square bound. In fact, you almost get to the conjectured bound, except that you have this annoying log influence term. So we show that the mean entropy of f at squared is at most influence times log influence. So I stated the theorem here for balanced functions, but there is a version for non-balanced functions. I just didn't want to make it too clumsy. But yeah, this is kind of close to the conjecture, but still we have this annoying logarithmic term. So the actual statement that we proved, and I'll soon state it, is actually more in spirit. It's more like that the Shannon entropy of the distribution is at most influence times log of influence, though we don't know how to show that. So I'll soon show you what we do know how to show, but it's somewhere in between. So to state that, I need a little more background. Well, so we defined this notion of total influence, and I told you that one of the names for the total influence is the average degree. And now I'm going to explain to you why that is. So here's the lemma, a very standard lemma that you can prove for yourself. If you look at the influence of the ith variable, then there is a very nice Fourier analytic formula for that, which is simply the sum of all of the squares of the Fourier coefficients of f among characters that contain I. And the proof, as I said, you just look at the function that expresses this influence, which is this difference function. You take the square of it, you take expectation, and you see what you get. So this is kind of the proof. But from that, if you take this equation and you sum it over all I, you get on the left side the total influence of f, and on the right side you get summation over characters, size of character, times f at s squared. And if you look at this equation, now you see why total influence is called the average degree, because again, you can think about this squared of Fourier coefficients as distribution, and then the right side is a weighted sum of the size of the character when the weight is with respect to the Fourier coefficients. So in a sense, this is the average degree of the function f. So let me make a side remark that will be important later. So from that, we already get that if the total influence of f is at most k, then most of the weight of f lies on levels below k over epsilon. So this is just a Markov bound. So this says that if we want to study functions with small influence, it may be wise to study functions of low degree. This is indeed something that we'll talk about soon, but this is just sort of a hint to what is going to happen. Okay, so now that we have this average degree formula, I can tell you an equivalent formulation of FEI, and then I can tell you the actual form of our result. So if you expand out the Fourier-Entropy conjecture using that formula, you get that the bound that you want to show is that this inequality on the slide holds for all Boolean functions f. And the theorem that we prove is that, well, this almost holds, except that instead of the size of s, you have to put the size of s times log the size of s. So again, this logarithmic factor appears. And actually, you can prove a stronger version of that, where you don't sum over everything, but over characters up to a certain size t, where t is something that you can choose. So this is really the main result that we prove, but I think that it's better to think about it as if it's the FEI, except we have this log term. So let me tell you some implications of this result. So first of all, we get a statement along the moral statement that I said above, except that again, we pay this logarithmic factor. So we can prove that if your total influence is most k, then your Fourier transform is somewhat sparse, meaning it is concentrated on 2 to the k log k many characters. So we can show some relation to agnostic learning of low degree functions. So this is improving some result of Gopal, Kalai, and Clivans. We can also get improved sharp-threshold results. So I told you that Bourgain and Kalai managed to prove some version of the sharp-threshold results without appealing to the Fourier-Entropy conjecture, and we managed to improve them slightly. And finally, which is something that is both nice and not nice about this theorem, is that, in fact, it's not really only true for Boolean functions, but rather there is a version that I'm not going to state now for bounded functions. So this is nice because, well, bounded functions is more general than Boolean functions. But in a sense, this is also kind of a bottleneck of our technique, because there are things that are true for Boolean functions, not for bounded functions. So one of the things is this logarithmic term. So it seems like with the current techniques, we'll not be able to remove it, but yeah. Okay. So if there are any questions, please ask me. Otherwise, I'm going to tell you a little bit about how such things are proved.
Just one question. For bounded functions, just the same inequality with extra log factor, right?
So not quite. So let me try to say how it works. Yeah, so if you look at this inequality with the, let's look at the mean entropy thing. So it says that the mean entropy is at most influence times log influence. So for bounded functions, what you would get is that you'd get influence times log of L1 influence of F. So there are various notions of influence. For Boolean functions, they're all the same. Depends on which norm of the derivative you take. Usually you take two norm, but here one of them would be two norm, and the other one would be one norm. So that's kind of the statement for bounded functions.
So total influence is in L2 times log of total influence is in L1, right?
Yeah, exactly.
Okay.
Yeah.
Also, if I can ask a question, in the Fourier-Entropy influence conjecture, it's a conjecture that it holds also for functions that are not balanced.
Yeah, so the issue is that for non-balanced functions, sometimes you have to normalize by the variance of the function. So if you take the correct normalization, then the conjecture is supposed to be true for all functions. But you may not even need to make this normalization. I don't remember off the top of my head.
Okay, thank you.
Sure. Okay. Good. So I told you about the basics. I told you what is the Fourier-Entropy conjecture, and I told you our results. And now I'm going to sort of give you a crash course on what hypercontractivity is and how do you use it to prove such results. So as I already said earlier, if you want to study function with low total influence, it means that you want to study a function with most of the Fourier mass lies on the low levels, on degrees of k. So you need to study low degree functions. So what can you say about such functions? Okay, so let's look at that. So we have some multilinear polynomial because we have that all of these functions that we look at are multilinear polynomials defined on the cube, and it has degree at most d. What sort of concentration type results can we show for it? Well, the most famous example in probability would be the case that d is equal to 1, you have a linear function, p, and the case where all of the coefficients are the same, and they're all 1 over root n. And in that case, we know a lot of things. We know that when we look at the distribution of values of p of x, it distributed roughly as a normal random variable with mean 0 and variance 1. And this is really an overkill. So this really tells us exactly what the probability is. But in particular, we can compute all of the moments of this. We can give tail bounds and anti-concentration bounds, and everything that you want is available. Okay, so let's generalize a little bit. Let us now look at still a linear function, but now the coefficients are not the same. So because the coefficients are not the same, this does not have to be a Gaussian random variable. So for example, you can take A1 to be 1 and the rest to be 0. Then again, you have this dictatorship function. This is not a Gaussian, but still, if you look at it, you can still compute all of the moments, you can compute tail bounds and everything that you want. So in particular, here is one thing you can show. This is a baby version of hypercontractivity. So if you have a multinode function of degree 1, and you look at its fourth norm, then up to constant, it's at most the 2 norm of p. And this constant is even something explicit, it's square root of 3. So this is really, if you take a couple of minutes and compute out this fourth moment, you will prove this result. And what hyperconductivity amounts to is a generalization of this fact for degree D functions. So it says that now if I have a degree D function, then the fourth moment of it is at most some constant that depends exponentially on D times the 2 moment of P. Okay, so this is hyperconductivity. This is a big name for something which is not immediately clear if it's supposed to be of any use. So let's try to interpret what this inequality tells us and how to use it. So here is a fact. Suppose I give you a function from the cube to -1, 0, 1, and I tell you that the probability that the function gets a non-zero value is delta, which is some very small number. Then I claim that the degree of this function as a multilinear polynomial must be at least log 1 over delta times some constant. So this is a fact, and now I'm going to completely give it an overkill with hyperconductivity. So here's the proof. So we know that by hyperconductivity, if I look at the fourth moment of P, then this is at most 3 to the degree of P over 2 times the 2 moment of P. And the point is now is that because P is -1, 1, 0 valued, I can completely compute what this fourth moment and 2 moment are. So the fourth moment is just delta to the fourth, and the second moment is just square root of delta. So now rearrange this inequality, I take a log, and I get that the degree of P is at least log 1 over delta.
Could you state something about the constant, any its range of values, possible values?
You mean the constant in the log 1 over delta?
Yes, correct.
Yeah, so I think you can improve. So the proof that I have here does not give the optimal constant. I think that you can improve it further, and maybe it's supposed to be close to 1, but I'm not entirely sure. But in any case, this is a true fact, but the proof that I showed you is a complete overkill for it. So why is that? Well, there is this very basic lemma called the Schwarz-Zippel lemma, which tells you exactly that. If you have a function that has degree at most k, then it cannot get any specific value with probability less than 2 to the minus k. Yeah. So this is the generalization of the fact that a degree D polynomial cannot have more than D roots, but this is adapted to the case of F2. Yeah, so I gave you this very complicated proof for a very simple fact, but what I claim is that actually you can get a much more robust version of this fact. So here is a robust version of this fact. So before you read this fact, let me tell you how you should think about it. So earlier we proved that if we have a function P that gets a non-zero probability, the non-zero value of the probability delta, which is small, then P is a high degree function. But now I'm going to tell you that, look, not only is it a high degree function, but almost all of its Fourier mass lies on the high degrees. So formally, the way you say that is, again, suppose I have this plus minus 1 zero-valued function, and the probability it is non-zero is delta, which is smaller. Then if I look at all of the Fourier mass below level 0.1 times log 1 over delta, this is much smaller than the total Fourier mass. So total Fourier mass is delta, but you get that the total mass on degrees lower than log 1 over delta is most delta to some power larger than 1. In this case, 9 over 8. Okay, so this is the robust fact, and this is really where all of the game of hyperconductivity and all of this KKL business begins. So how do you prove it? Well, let's see. So let's look at the low degree part of the function. This is G. And note that the thing that we want to bound is simply the inner product between G and P, because this really gives you the low degree part of P. Now there is this very standard and nice trick that people use in this area, which is a combination of Holder inequality and hyperconductivity. So you can bound the inner product between G and P by the fourth moment of G times the third moment of P. And then you can bound the fourth moment of P using hyperconductivity by the second moment times some exponential factor in the degree of G. And now the point is that when you are in the two norm, you can move from the two norm of G to the two norm of P by a Parseval equality. And now that you have expressed all of the norms using P, because it is a plus minus 1 and 0 valued function, you can just compute all of these norms. The two norm of P is delta to the half, and the 4/3 norm of P is delta to the 3/4. So you just plug that in, and you get the result. Okay, so you have to do the math. The point is that the product of these two norms is much less than delta. So if you take the degree to be small enough constant times log 1 over delta, you get the result that I said. And if you do the math, you see that what you get is what I said. Okay. So this is where all of the game begins. Now we have this robust fact, and now I can tell you how this fact relates to KKL and free root. Namely, I'm going to show you how to prove KKL. So let's recall what we're trying to prove. We're trying to prove that if the total influence of F is at most K, then there exists some coordinate I with influence at least 2 to the minus K. Well, let's assume for contradiction that all of the influences are small. Let's say that they are all at most e to the minus 100 times K. Okay, so now, so I have on the slide a robust fact, and I have this assumption that all of the influences are smaller. And I need to connect these two facts. I need to make some interesting conclusion. So I want to design a function that the probability is not zero relates to the influence of I, and then I can, using the robust fact, say something about its degree. So the function that is natural to consider is the discrete derivative of f with respect to I. So this is the function partial I f, which is defined as the difference between f of x and f of x with the ith bit flipped. And for normalization purposes, I divide by 2. And you need to make two observations. First of all, the values that the function receives is indeed plus minus 1 and 0, because either f of x is equal to f of x plus I, or they're different, and then this is either minus 2 or plus 2. So that's one fact. So this is, and secondly, the probability it is non-zero is exactly the influence of the ith variable. because this is exactly how influences were defined. So we're in game. We have this function. We know that it has the right range, and the probability is non-zero is small, because this is our assumption. So now we can say that its degree is high, but let's look at its Fourier transform. So if you plug in the Fourier transform of f and of f with the ith bit flipped, you will get that the Fourier transform of the derivative of f with respect to I is this sum. So roughly speaking, it's its derivative in the really standard terms. You take all of the monomials that contain the ith variable, and the rest of them you throw away. Good. So as we already observed, the probability that derivative is non-zero is exactly the influence of the variable I at f, which is small. So now we can apply the robust fact and say that, well, the total mass that lies below level 10k in the derivative is at most the influence of the function at variable I to the power 9/8. So that's just the robust fact. And now we can pull out one factor of influence of I and replace the rest by the band that we have and say that this is at most e to the minus 100k/8 times the influence of I. Okay, so we're almost done. So now we look at what are the Fourier coefficients of the partial derivative of f, and as we observed, these are all of the Fourier coefficients that contain I. So I can write it exactly like that. And now I'm ready to take sum over I. So now I take a sum. On the left side, I get all of the characters that are of size at most k, multiplied by something, which is at least 1, but never mind that. And on the right side, I get e to the minus 100k/8 times the sum of all influences. So sum of all influences is total influence, which is most k. So I get exponentially small in k times k. So this is in particular less than 0.1. So what is it say in words? It says that if we look at the Fourier spectrum of f, almost all of the mass lies above level 10k. Only 0.1 of the mass lies below that. And if you think about it, that means that the average degree is at least the remaining of the mass times the very smallest character there. So that means that it's at least 0.9 times 10k, which is larger than k. So this is a contradiction to the fact that the average degree of f is at most k. Okay, so maybe it was a bit too quick, and maybe a bit, yeah.
When you sum up over I, you shouldn't like multiply square by s.
Yeah, so you should, but I'm giving that up. I'm saying I only want to upper bound something weaker. So s is so yeah, s is at least 1. So yeah.
Once again, why we come to contradiction? Why we came to contradiction?
Yeah. So let me say it again. So we proved that the total mass of f below level 10k is at most 0.1. So it means that if you look at all of the Fourier coefficients above level 10k, this is at least 0.9. So now if you look at the summation of size of s times Fourier coefficient squared, this is at least this 0.9 times 10k, because at least 0.9 of the mass is level 10k and above. So this says that the average degree is at least 9k, but we know that the average degree is exactly the same as total influence, which you assume to be at most k. So this is the contradiction. So yeah, so really what this argument shows is that if all of the influences, all of the individual influences are smaller, then what you get is that the total influence is larger. It's written in a contradiction way on the slides, but this is really what it shows. Yeah. So, so I hope that this was clear. So this was this is kind of how arguments work with hyperconductivity in this business. So, and next, I'm going to tell you how you take some argument like that. What would be the dream of applying it in a different setting? And I'll tell you one word or two words about how you actually go about doing that. So really, looking at this argument that we saw a bit more generally, what you get is the following reformulation. This is an argument that tells you that if you know that all of the influences are small of the function, then you can show that the function does not have a lot of mass on the low degrees. In particular, you can show that the total mass of f on degree at most d is something like delta to the some power times exponential in d times the total influence. And you should kind of ignore this total influence term. You should really contrast this delta and exponential in d. So one way to think about it is if you have all of the influences that are small, this is a correlation bound of f against all low degree functions. And once you play around enough with these things, you realize that the bottleneck in all of these arguments is this exponential in d bound. This is what gets you stuck in the logarithmic barrier, because once d is above log n, you get some factor of n, which you can never win. So what do? In general, it is tight, and we don't know what to do. So what can you do? So the first and kind of only case that I know that it will be something beyond this logarithmic barrier is this Bourgain-Kalai paper. So it's a very interesting paper, let's put it that way. It's not an easy paper to read. It took me several years, but they do manage to use symmetries of functions in order to bypass this logarithmic barrier. And drawing inspiration from their paper, and actually in a project that sort of whose goal was sort of to understand what they did, we also managed to bypass this logarithmic barrier, and meanwhile we managed to improve the result. So in one sentence, this is if you want to take one catchphrase from this talk, is that sometimes it's good to do a random restriction before you apply hyperconductivity. And then some good things may happen. So I didn't tell you what random restrictions are formally, and I'm not really going to tell you that. But random restrictions is a technique which is very prevalent in the area. And roughly speaking, what you do is you choose a set of coordinates randomly, you fix them to some values, and you think of the rest as variables. And the effect of this operation are very nice. You can sort of hope that something like that decreases the degree of the function. And in a sense, this is something that indeed happens. And this is the intuition to why you expect something like that to be useful sometime. So why is that? So again, as I said, the random restriction, you take a small fraction of the variables, say alpha of the variables. The rest of the variables you fix to some random values. And these alpha variables, you keep it as variables. then you can sort of expect that if the degree of your function was d, the degree reduces to be alpha times d, which is much smaller. So now you can say, okay, maybe I do randomization, then I apply hyperconductivity. Now that my degree is smaller, maybe I can get something better. And indeed, you can try to do something like that for KKL and all of these theorems. But the issue is the following. So recall that for this KKL stuff, our assumption was that all of the influences are small. And kind of the issue is that if I have a function whose influences are small, and I take a random restriction, then the influences need not be small anymore. And indeed, there are good reasons to expect some of them will become large, where most of them will remain small. So you cannot simply apply a random restriction and then do the same old arguments again, because you expect there to be some high influence variables. So what do? Well, you have to think what to do. But let me tell you that you can do something, provided that all of your Fourier coefficients are small. So it is true that there can arise variables with high influence, but you can prove that there are not too many of them. And if your Fourier coefficients were small originally, the total contribution of these things would not be too much. So making these statements formal would require a lot of time, so I'm not going to do that. But this is really the guiding principle in our proofs, and this is what we do. So as I said in this talk, this randomization business is useful to prove Fourier concentration bounds, but also it's useful for a bunch of other things. So for example, using just random restrictions, you can prove some nice isoperimetric results. So recently there was this proof by Ronen Eldan and Renan Gross of this Talagrand inequality, but actually it turns out that you can prove it just by random restrictions and some very standard results in the area. And yeah, it's still open whether we can use such techniques or any techniques at all to prove the Fourier-Entropy conjecture or the mean entropy conjecture. And also a question which is interesting, in my opinion, is to prove an appropriate version for the p-bias measure. But here you should think of p as something that is close to 0. So in this context, the kind of right analogy would be that the maximum of the Fourier coefficient square times p to the minus s would be large, but we don't know that. And also we don't know that with the logarithmic factor. And finally, there is this Minzer conjecture, which is considered important in TCS, and it would be nice also to resolve that. So that's all I have to say. Thank you.
Thank you very much, Tor. That was a great talk. Are there any other questions? Okay, then I'll ask one question. Is there analog of Fourier-Entropy conjecture for bounded functions? And if you just plug Boolean, you get Boolean Fourier-Entropy conjecture. But in general, there is some kind of more inequality for bounded functions. Are you aware of something like this? Not necessarily Boolean, just bounded by absolute value is bounded by 1.
Yeah, I understand. So I think that there are versions of this statement. Some I don't remember them off the top of my head, but similarly to what I said before, you can often try to play around with statements where instead of total influence in L2, you put L1 influence. And then for Boolean functions, there would be no difference. But for bounded functions, L1 influence is larger than L2. So that's something that is worth considering. So, right, so the objection to the entropy conjecture by itself for bounded function would be a function like sum of xi over n. And I think that this L1 thing fixes that. But if it doesn't, then... So anyways, I think that there is some version, but I don't remember it off the top of my head.
Okay, thank you very much. There is Wahlberg has raised hand.
Yeah.
When I become Wahlberg for you, Pata. Okay, so you just mentioned that by this method you can, by your method you can reprove Eldan and Gross result. Yes.
Yeah, but it's much simpler than that. You don't need you just need random restrictions and some tail bound for yeah.
Right, because like we know that by our formula we can also do that, right?
Yes.
Yeah.
It's funny.
Is this random restriction written somewhere, or it just some people know about this?
It's a long story that I can tell you after the recording is over.
Okay. Okay, any other questions? Okay.
So in this open on this slide, the last lines, you just consider measure not 1/2, but P1 over P and do all these averages over this measure?
Yeah, so in this business, whenever P is bounded away from 0 or 1, it's kind of the same. I think that then everything works exactly as is. So my point in the second question is, what if you take P which is 1 over root n? So then you need to define the appropriate basis and all of that, but then we don't know this. Then these things are, so there are a bunch of issues there with the hypercontractive inequality by itself. So if you know there are these Boolean booster theorems and all of these things that address this regime, but we don't have an analog of the mean entropy.
Haunan has a question. Haunan?
Yes. So you have also a mini entropy version of the conjecture. So do you have some kind of range entropy which interplays mini entropy and the Euro entropy?
You mean in the p-bias case?
Yeah.
Yeah, so the Shannon entropy kind of analog would be that not only is there a Fourier coefficient like that, but the function, almost all of the mass of the function lies on this. And I think that if you take a log of this and like log of 1 over this and do the right sum, you'd get the kind of right analog of the Shannon thing. But the moral statement would be that almost all of the mass of lies on characters that satisfy that pp to the minus s times Fourier coefficient squared is at least exponential in influence.
Okay, thank you.
Sure.
Any other questions? Okay, if there are no questions, let's thank the speaker again.
Thank you.